Hello everyone, and welcome to the second part of the design of continuous one-way slab. Uh, in the first lecture we have seen three kinds of we have seen the 6 steps. The 6 steps are the effective depth, effective span, maximum dead load and live load, check for depth, and area of steel in tension. So we have completed the first part of the design of continuous one-way slab, and we will now focus on the part 2, which contains the continuation of the part 1, which includes a shear check, then deflection check, development length, distribution bar, and figure for the one-way continuous slab. So this was the question that was solved in the part 1 of the design of continuous one-way slab, and these are the given datas that we have seen in the part 1. You can also, if you have not yet seen the part 1, then must watch the part 1, and then you may continue with the second part of the one-way slab. So up to 6 steps we have already completed, and the 6th step was the about reinforcement. So we have provided the diameter and spacing of reinforcement as per the area provided. So the 7th step of the design of continuous one-way slab is to check for shear. So before starting the check for shear, we have to write the coefficients of shear force or coefficients of shear for dead load and live load. So these two we have to write. So you can move on to the IS 456 page number 36. On page number 36 you will have the table 13, which provides the coefficients for shear. So here you can see this is dead load and here it is a live load. So it says that at end support dead load coefficient should be 0.4 and the live load coefficient should be 0.45. So at end support, this is the end support. So at end support the dead load coefficient of dead load is 0.4 and the coefficient of live load is 0.45. so at both end I have placed this value from this IS 456 page number 36 table number 13. Now let us move to the second. So at this support next to the end support, it talks support next to the end support, which means this support and this support. There are two. So first it is outer side and second it is inner side. Outer side means this outer side and this is inner side. This is inner side and this is outer side. So let us first see about the outer side. Outer side has a value of dead load as 0.6 and imposed load or live load as 0.6. So we have written 0.6 over here on the outer side. Now let us see about the inner side. So inner side has the dead load coefficient as 0.55 here, and it has the live load coefficient as 0.6. So 0.55 and 0.6 and 0.5 and 0. Inner side. So we have to, yeah, it's okay, 0.6. So here I have made mistake. It will be 0.55. So next it says that at all other interior support, if in case we have one support over here, so at that support we have to write this coefficients, but in our case this will not be included, so we don't have to take in this consideration. Now we have to calculate VU, which means shear force. So we have to calculate shear force for all this first 1 2 3 4 5 and 6. We have to calculate for all. First we will calculate for the end of the span or the end support. So we will calculate first for this one and for this one. So for that, for calculating the VU, the equation is provided like alpha D, or we can say coefficient of dead load, into the dead load into its distance plus coefficient of live load into its its distance or its span, or we can say length. So the coefficient of the dead load for the end span is 0.4, as we know. Here we have calculated as we have found as 0.4. So moving on to so here we have found as 0.4. so here the coefficient will be 0.4. So the dead load is given. So the dead load is here 6 kilonewton per meter. So here we have dead load as 6 kilonewton per meter, and its distance. So the span has a length of, or we can have a distance of 3.5 meter. So 3.5 meter plus we have to see now second for the live load. So the coefficient of live load is 0.45 and into its load is 4.5 over here, and its distance is 3.5. So we have get the VU as 15.49 kilonewton at end. So we will have here value of VU as 15.49, and here we will have 15.49. Now moving to the internal support. Now talking about this part of this part and for this part. Similarly, we have to do coefficient of live load, or we can say coefficient of dead load into its distance plus coefficient of live load into its distance. So 0.4 into 6 into 3.5 plus 0.45 into 4.5 plus 3.5 into 3.5. So we'll have the value of that point will be 22.05 kilonewton. So we will have 22.05 over here and 22.05 over here. Now we will move on to this values. So now for that it will be 0.5 into 6 into 3.2 its distance, and plus 0.6 into 4.5 into 3.2. So we will have the value as 19.2 kilonewton. Now from this all values of VU, we have to select one maximum value. So highlight the maximum value which will be used in the further calculation. So VU, so tau V. To calculate tau V has an equation known as tau V is equals to VU upon BD. So VU, this VU we have to take as the maximum value which has been obtained. So with the value has been 22.05 into 10 raised to 3 divided by B. B means 1 meter. So 1 meter will convert it into mm. So 1000 mm into depth, which we have calculated in the first step, which is effective depth, we have found as 95 mm. So we'll have the value of tau V as 0.232. Highlight this value. We will use this value for checking the shear check. So like this we have founded the values of VU at these supports depending upon the values of coefficient of live load and dead load. So at this support the it is maximum, so this value we will be used in the further calculation. So next we will calculate to check the shear. We have to calculate tau C dash. To calculate tau C dash, you have to go to page number 73 of IS 456-2000 and table number 19. At that you will for calculating the tau C, you need two values, which is grade of concrete, which is already have given in the question, and the second value you need is a percentage of steel. So the main target is to calculate the to find the percentage of steel. So percentage of we have the formula that percentage of steel is equals to area of steel in tension into 100 into upon B into D. So the value remains unknown is area of steel. So we have to first known the area of steel. So area of steel we will find from this. We know that at this support we have provided 10 diameter bar, 420 center to center, 8 diameter of bar, 420 center to center, and 8 diameter of bar, 420 center to center. We will use these three kinds of reinforcement. So here we have used 10 dia 420 center to center, 8 dia 420 center to center, and 8 dia 420 center to center. So by this I have calculated the area. So for 10 dia 420 center to center, its area is 186.9, plus for 8 dia 420 center to center, its area is 119.67 mm. So by mm square, by adding these three values, we will have the total area provided as 426.24 mm square. So we will place this value of area of steel in tension provided in the equation of percentage of steel. So we will have the value of percentage of steel as 0.45%. Now this value will be observed in the table number 19, page number 73 of IS 456-2000. At that the value comes between 0.25 to 0.5, so we have to interpolate and we have to see the grade of concrete. So the grade of concrete is M25. So after interpolating it, you will get the value of tau c dash as 0.464. Now next what we have to do, we have to find tau c. So tau c is equals to k into tau c dash. We have already calculated tau c dash over here, so the tau c dash value is 0.464. so we have already provided value of tau c dash as 0.464. now value of k will depends upon the depth of the slab, overall depth, capital D of the slab. So move on to the page number 72 of the IS 456-2000, where clause number 40.2.1.1, where it says that the design shear strength for concrete shall be tau c dash into k, where k will be depend on the depth of the slab. So in our case the depth of this slab is 120 mm, so which is less than 150. So we will use the value of k or the coefficient as 1.30. so we will multiply with 1.30 and we will have the value of tau c as 0.6 MPa megapascal. So we will check that the tau c, we have calculated tau c over here and tau v over here. We have calculated tau v over here. So tau v is greater than tau c, so no shear reinforcement are required. If this condition doesn't satisfy, then we have to provide a shear reinforcement. So we have completed the check for shear and we have proved that the no shear reinforcement are required. Tau c is greater than tau v. So step number 8, check for deflection. So check for deflection is done at the center of the span only. So we will check on the depending upon the bending moment have on the center span. So here is a center span moment, here it is a center span moment, and here it is a center span moment. Above from this, the maximum value we will consider for the design for the check of the deflection. So the maximum value of for the bending moment is 11.63 kilonewton meter. So we will check the deflection by using the higher value of bending moment, and we will also see the value of or the reinforcement detailing or the reinforcement provided at that location. So first we will use the value of bending moment in kilonewton per meter will be 11.63 because it is maximum of these three values. So for it, first it will be for initially starting it, we will do L by D allowable. We will firstly we will find allowable and we will compare it with actual. So first step is to check. First step is to find the allowable deflection. So allowable deflection we will find as L by D allowable is equals to 26, which comes from the IS 456, and it is a continuous. So it will be 26 into KT, KC, KF. The value of KT is unknown, so the value of KC will always be remain 1 and KF always will remain 1 only. So first of all we have to calculate percentage of steel. So for calculating, we know that percentage of steel formula for percentage of steel is AST provided into 100 upon BD. So for that we have to first know the area provided. So we know that we have provided 10 of 210 center to center. So we will use that and we will find area provided. So I have found the area provided as 373.99 mm square. So by using it, I have placed the value of AST over here and found the percentage of steel as 0.393. So we can consider as 0.40 percentage. This value will be used for obtaining the value of KT. So for obtaining the value of KT, the another thing we have to find is the value of Fs. So the equation of Fs is already given in the IS 456 page number 38 and the graph or the figure number 4. So over here the value or the equation of Fs is provided over here. You can take from that. So the value of Fs is 0.58 into Fy into area required upon area provided. So we have to, so provided is over here, so we have just find it the provided, so we have placed over here, and required we have calculated in the fourth step of the on the part 1. So by this we have found the value of Fs as 235.39. Now this two value we have to remember, percentage of steel as 0.4 and a value of Fs as 235.39. Now come on to this graph. Here it shows this percentage of steel of reinforcement. So we have found the value as 0.4 and the value of Fs which is 235.39. So it comes between this. So we have to interpolate and find the value of modification factor, which we have found as 1.4. So we have find the value of KT as 1.40. Now we have to multiply by this and we have found the allowable deflection as 36.40 mm. Now it's time to second part for the actual. So actual deflection is equals to L by D. So L, the total length is, maximum length is 3500 mm divided by small d, which is effective depth. We have calculated from the first step, which is 95 mm. So we have find the actual deflection is 36.84 mm, where actual deflection is less than or equals to 36.40, which is actual deflection is less than allowable deflection, which means it is safe over the deflection. So we can say check for deflection is okay. If the actual deflection is more than the allowable, then the check will fail and you need to redesign the whole example. So now the step number 9, which we will see the development length. So there are two formulas. First it shows the formula for the fixed support, and the second it shows for the simply support beam or slab, we can say. So in our case there is simply supported slab, so we will use the equation for the LD as LD is equals to, here it will be is equals to, LD is equals to M1 upon V plus L0. This all terms will be explained in the further discussions. So LD, first we'll see the value of LD. So the formula for LD is already provided in the page number 42, clause number 26.2.1 of IS 456 2000. So IS 456 provides the value of LD as 0.87 Fy phi upon 4 tau BD. So already 0.87 into Fy we have grade of steel is provided as 415, and diameter, so diameter of bar we have taken as 10 mm and 4. Now it's time to see the value of tau BD. So tau the value of tau BD you will get from the table, or you can say clause number 26.2.1.1 of IS 456/2000, page number 43, which depends upon the grade of concrete. So grade of concrete is 25. So we have the value of tau BD in Newton per mm square as 1.4. So we have placed 1.4, and as it is HYSD steel, we have to multiply with into 1.6. You can read this clause 26.2.1 where the multiplication factor for the HYSD steel is provided. So the value of LD is we have already found as 402.9 mm. Now let us move on this thing. So for that thing, LD is less than m1 upon v plus L0. So now we will see the value for m1. So the value for m1 will be mu by 2. This mu, which we have calculated kilonewton into meter, we will take the maximum bending moment at overall section. So the maximum value of bending moment is 11.63. divide by 2, because it will transfer the half moment at the one support and another half moment at the another support. So we will divide the moment with 2. So we will have the value of m1 as 5.81 kilonewton meter. So let us move on the value for L0. So L0 is equals to BS, which means the width of support divided by 2 minus x2. x2 means clear cover, plus 3 times the diameter. So why the 3 times diameter comes as for 90-degree bend. For 90-degree bend, we have to add the value as 3 times the diameter. So by placing the value of BS as 300 divided by 2 minus clear cover, we have provided 20 plus 3 into diameter of bar 10 mm. So we have find the value of L0 as 160 mm. So let us place the values in this equation. So the value of LD is 402.9 as per the calculation, which is less than or equals to m1 upon v plus L0. So we will find the m1 value of m1 as 5.18 into 10 raised to 6 upon v. So value of v we will take as the minimum value. So over here we have calculated the value of v. From this we have to take the minimum value. So minimum value is over here. For checking for it, we have to take value of VU as minimum. So we have provided the minimum value of shear and plus L0 according to the calculation. So we have found that the LD, the value of LD is less than 535.80. So it is okay. So check for deflection where VU is less. So where VU is less, that at that point we have to check the development length. So it says that development length, the requirement of development length is okay. So we don't have to provide any additional length for the development between two reinforcement. So it is okay. Now the last but not the least, the step number 10 is to as the distribution bar. So for calculating the distribution bar, the formula is provided for the area of steel in tension as a minimum steel is 0.12 into B into capital D upon 100. So 0.12 B is equals to 1 meter. So we will convert into mm. So 1000 into capital D, which means overall depth as 120 mm divided by 100. So we'll have the value of area of steel, minimum steel, as 144 mm square. So we will provide the lesser diameter as lesser as possible, 8 mm diameter of bar. So we will find that how many numbers of bars required in per meter. So number is equals to capital AST, which means AST minimum, which we have calculated over here, and small AST as area of steel. So we have found the number per meter, which 2.86. Now we will have the spacing. So the spacing is equals to 1000 upon number. So we have found the spacing as 349.06. So we have placed the distribution bar as 8 diameter, 350 center to center. This spacing will be adjust as per the reinforcement coming from the different spans from the right side and left side. It can be arranged as per the requirement. So step number 11, which shows the figure. So we have seen the provided, this is the bent up bar, which will be alternative from here to here, which will be like this, and from this span it will come from here to here, and alternative bent up from here to here, and above it the we can say the extra top bar will be provided connecting these two reinforcement, blue and red, and these are the dotted are the we can say distribution bar, and the distance for bent up and bent ups and all are provided in the figure. You can use these equations and for the bent up and from the center of the span or the center of the wall. Here it shows the plan. As I told, this is the alternative bent up, so we will bend from here and will remain straight over here. We will, which for second it will remain straight over here, it will bend over here. This will be alternative bent up. Similarly, one of the bent up will be provided here, and similarly like this. On this second span, for the second span we will see here it is the bent up, so here it will be bent over here, and the another bent up is seen over here. We will like this, and to and between them the we can say the extra top bar here it is provided, and also to connect that main bars we have to provide the distribution bar. So here it has been shown in this direction. There are distribution bar 8 dia, 320 center to center or 350 center to center in this direction. So here we complete the whole design of continuous one-way slab, which we have seen the starting from effective depth, and then effective span, then maximum bending moment and shear force, then MU and AST, then reinforcement, check for shear, check for deflection, development line, distribution bar, figure for slab. So thank you for watching this design for continuous one-way slab, and I am also processing for the design of continuous two-way slab. And like, share and comment, and let me know if you want any other kinds of videos, and you can watch the part 1 also for more clearance. Thank you.